Hello students, welcome to the online session on basic electronics. Today we'll be learning about BJT and its applications. So the contents we'll be learning today will be BJT as an amplifier, BJT as a switch, simple application of transistor switch, feedback amplifiers, properties of negative feedback amplifiers, feedback topologies, and you can refer page number 12 to 18 in your notes. So let's quick revise what we have studied in the previous session, that is about BJT. So BJT is a three-terminal device with base, collector and emitter as the terminals. It is always called as a current control device because the base current will control the current flow from collector to emitter. Okay, so we have two different types of BJTs, that is PNP and NPN structure. BJT gets its name bipolar junction transistor because here the electrons in NPN and holes in PNP are the majority carriers, and because of the flow of these two majority carriers it is called bipolar junction because there is a junction formed by sandwiching two N layers or two P layers in between N and P. Transistor comes from the name transferred resistor, whereas the resistance is transferred from a low resistance to high resistance. Okay, and also we have seen that there are three different configurations in BJT, namely common collector, common emitter and common base. In most of the cases, we are using common emitter configuration because of the high power gain. Also, we have different modes of operation, say active mode, cutoff mode and saturation mode, depending on the external biasing, that is how the input and output terminals are biased. Now let's go into the study of BJT and its applications. So first application of BJT, very important, is BJT as an amplifier. So amplifier means it amplifies whatever the input signal given, or we can say that it will strengthen the weaker signal. Okay, so in case of BJT, its one of the main application is amplifier. Okay, so a transistor acts an amplifier by raising the strength of a weak signal. We have to note here that we have to give a DC bias voltage applied to the emitter base junction makes it remain in forward bias condition. Thus, a small input voltage results in a large output voltage, which shows that transistor can work as an amplifier. So, main important concept is that BJT transistor amplifies current because the collector current is equal to the base current multiplied by the current gain. We have already seen that the equation that the collector current is equal to beta times IB. IC is equal to beta times IB shows that we can amplify the collector current depending on this beta factor, and also we know that beta is always greater than 1. So beta times IB. So because of this we can get a high output signal. The base current in a transistor is very small compared to the collector and emitter current. Because of this, the collector current is approximately equal to emitter current. We know that base region is very lightly doped, and because of this, the current flow is very minimum, right? The base current is very small. So we can also say that the collector current is approximately equal to the emitter current. So here the main concept you have to understand that when BJT is used as an amplifier, the main purpose is whatever the input signal is given, it has to be amplified. Okay, so let us see what is a circuit diagram of an amplifier. Okay, let us consider this circuit. Now all of you know that this symbol is of an NPN. NPN, because the direction of emitter current is outwards. Okay, so it is an NPN transistor. Here we are giving a DC bias, okay, that will support this particular BJT to work in active mode. So we all know that BJT will operate in three different modes. What are the three different modes? Active mode, cutoff mode and saturation mode. How does a BJT work in active mode? Whenever the base and the emitter works in forward bias and collector and base works in reverse bias, then this kind of mode will make it work in an active mode. Whereas in cutoff mode, both the input and output sides will be in reverse bias. Whereas in saturation, both will be forward bias. To make BJT work as an amplifier, we have to configure it to work in active mode. So because of this, we are going to give the external DC bias VBB, which will forward bias the base and emitter, and VCC will reverse bias the collector and the base. Okay. So now if you see this as the common emitter configuration, here emitter is common between the input side as well as the output side. Okay, so here emitter is common to input as well as output. That is why this is used in common emitter configuration. So if you see here, the base and emitter is forward biased, collector and emitter is reverse biased. Now here we have a input resistance, say RB, that is the base resistance, and output resistance RC, that is the collector resistance. Also we can find that there is a capacitor placed and we have a AC input signal. So the main purpose of the circuit diagram is whatever AC input signal we are giving, that will be a weaker signal or a small signal, it has to be amplified and we have to get the output. Okay, so why is this coupling capacitor required? This capacitor is working as a coupling capacitor because we are superimposing now AC and also we have DC here. Okay, so we have to amplify AC signal, not DC signal, right? So because of that, it will act as an open circuit for DC, or it will not pass DC components but it will pass AC components. That is why placing a capacitor in series will make this AC input signal get amplified at the output. So this DC bias is very important because you have to know something called as Q point. That is also called as quiescent point. Okay, what is the important purpose of Q point or quiescent point is? It is the operating point of the device. Okay, the Q point will show you the steady state DC voltage or current at a specified terminal of an active device. Okay, now we know the common emitter output characteristics follows like this, right? So output current IC with respect to the output voltage VCE, where we are keeping the input current at constant. Okay, so if we draw the DC load line like this, okay, so we get different types of operating points. Okay, say here we get operating point, here we get different kind of operating points. Okay, so which is the best suiting operating point so that we get the full input signal without getting clipped? Okay, so if you see here, this portion is much into breakdown region. So if you take this as operating point, chances are getting that the output will get clipped. So here also, if you see, take this region also, it is nearer to the saturation region. Okay, so likewise we have to take a suitable Q point, say this point. So if you take this point, we can say that it is almost a steady state, and here we will get the full maximum swing. in the output. Okay, so depending on this Q point, we will give the biasing. Okay, so here it is 30 microampere. So we will give the voltage such that it will produce a base current of 30 microampere, so that we have a steady state point, so that there is no fluctuations. Okay, there is no variations. Okay, and we get the proper output without any clipping, right? So because of that, Q point is very much important. To get the Q point, we have to make proper approximate it to which value it should be biased. Okay, I hope you understood why we are biasing it and at what region we will be biasing it, at what point we will be biasing it. So that point, that is called as Q point. Q point. Okay, so I hope you understood the operating point of a common emitter, which will allow the output to, which will allow whatever the input we get to required to amplify the output will not be clipped in any ways, or will not be having any variations. We want the full swing output. Okay, so if you consider this, now you understood why are we using VBB. Okay, it will produce the IB, how exactly this BJT should work at that particular Q point. Okay, so the coupling capacity, you understood that it will allow only this input signal to pass through the circuit. Okay, so if you see here, this is V in. V in means what? It is the input signal. So it is a AC signal, so sinusoidal signal. Okay, sinusoidal signal we have, and it is biased at a point VBB. Okay, so Vs is the source voltage. Okay, source voltage. Now if you see at the output, 100% it is amplified, right? This is a small weaker signal. Here it is a larger signal which is amplified. Okay, so output is taken across VC, so this is the voltage across the collector, that is VC. Okay, now if you see properly here, the output is out of phase here. It is out of phase. Why is it out of phase? Because you can see that the direction of the current is from collector to emitter. That means opposite to the load. Okay, so that's why we get an inverted output. So always remember, when you are writing BJT as an amplifier, the output will be inverted version of input. It will get amplified, 100% it will get amplified, but it will be out of phase. Okay, so I hope you understood the circuit diagram. So here we are making use of a NPN transistor in a common emitter mode and common emitter configuration, and it is working in an active mode. That is why base emitter is connected to the forward bias is forward biased, and collector emitter is reverse biased. Okay, we are placing a capacitor such that whatever the AC signal is completely passed into the circuit without getting the without getting the DC components into it. Okay, so the Q point will be decided by the DC bias voltage, how we set up, and depending on that the base current, it will control the output voltage. So the important parameter we have to understand here is collector current is directly proportional to the base current, or collector current is equal to beta times IB. So because of taking that advantage, we can amplify whatever the input, that is input current, that is base current. Okay, so here let us see the DC bias voltage VCC is connected to the collector through the collector resistor RC. The AC input voltage produces an AC base current, which results in a much larger AC collector current. That means it is getting amplified. The AC collector current produces an AC voltage across RC, thus producing an amplified but inverted. This is very important, students. Output will be inverted, amplified but inverted. The forward bias base emitter junction presents a very low resistance to the AC signal. This internal AC emitter resistance is written as R-E, which is in series with RB. Okay, so here the forward bias emitter junction, here forward bias junction of this emitter. So here it produces a very low resistance because it is this emitter junction is base emitter junction is forward bias. So it is producing a very low resistance, and that is denoted by R dash E. Okay, so the internal AC resistance denoted by R dash E. It is providing a very low resistance. Okay, so now let us see how to get the equations. So the AC base voltage is given by VB is equal to IE into RE dash. So we all know that according to Ohm's law, we know that V is equal to IR. So the base voltage VB will be given equal to what is the current that is flowing, that is IA, and what is the resistance is given by RE dash. Okay, so this is the base voltage VB is equal to IE into RE dash. Now if you see what is VC, VC is nothing but IC. The current is flowing is IC, and what is the resistance? IC into RC. Resistance is RC. Okay, so VC will be equal to IC into RC, and VB will be equal to IE into RE dash. Okay, so the AC base voltage is given by VB is equal to IE RA dash, and the AC collector voltage VC is equal to the AC voltage drop across RC, and is given by VC is equal to IC RC. Also we know that IC is nearly equal to IE. Therefore, the AC collector voltage can be given by VC is equal to IE into RC. Okay, so if you see here, IC is almost equal. Since the base is small, we are replacing IC by IE. So we get the equation IE into RC. Okay. So since voltage gain is defined as the ratio of output voltage to input voltage, what is output voltage? Output voltage is VC. What is input voltage? Input voltage is VB. So we will take the ratio of it, we will get the voltage gain. So if VC we have got it as IE into RC, and VB we know that it is IE into R dash E. So the voltage gain can be designed by taking RC divided by R dash E. So what is the value we take here, depending on that we will get the gain of the amplifier. Okay, so the main important equation AV is equal to RC divided by R dash E, because when we substitute VC it will be IE into RC, when we substitute VB it will be IE into RE dash, and IE will get cancelled, and because of that you will get A is equal to RC divided by R dash E, where AV is the voltage gain. What is RC? RC is the collector resistance. What is R dash E? R dash E is the internal ammeter resistance or AC resistance. Okay, I hope BJT as an amplifier is clear for you. So here very important factor is it is working in active mode. Okay, and it is in common emitter configuration. Okay, and we are getting the gain which is equal to RC divided by R dash E. Okay, and the output will be inverted with respect to input and amplified. Next, let us see the one more application, BJT as a switch. To make BJT to work as an amplifier, we used active mode. But to make BJT to work as a switch, we have to use either cutoff mode for open switch and saturation mode for closed switch. Okay, cutoff mode means it is an open switch. Okay, so in that case IB will become 0. Saturation mode means it is a closed switch. Okay, so let us see how we are making use of a BJT as a switch. So BJT, to work it as a switch, first we have to make the transistor work in cutoff region. Okay, so in case of cutoff region, what happens? In case of cutoff region, the IB is equal to 0, right? IB is equal to 0 means what? This BJT is working as an open switch. Open switch means what? The output will be, the output is nothing but VCC itself. That is the maximum voltage, because there is no drop, there is no this circuit is open. So whatever the output voltage, the voltage that will give, given as the output. Okay, whereas when it is making work as a saturation, what we are doing here, VBB will be given, so IB is there. So because of that, this is working as a closed switch. Because of that, what happens, the output voltage taken will be, there will be, it is a closed switch, so continuous, there will be drop across this. So because of that, output VC will be equal to 0 because it is a closed switch. So whatever the voltage, that will be directly, traveling through this, and there will be voltage drop across this closed circuit, and that is connected to the ground. So VC will be equal to 0. Okay, so this is how we can make it work as a switch. In first case, to make it work as an open switch, what we will do, we will give input as 0 volts, or it is in cutoff region. To make it work in saturation region, we will give plus VBB. Okay, so let us see the working. Okay, so in this condition, there is ideally an open between collector and emitter as indicated by the switch equivalent. In figure B, the transistor is in saturation region because the base emitter junction and base collector junction are forward biased, and the base current is made large enough to cause the collector current to reach its saturation value. In this condition, there is ideally a short between collector and emitter as indicated by the switch equivalent. So very important, when it is in cutoff means VB is input voltage is 0 or IB is 0, right? So the base emitter junction is not forward bias, hence transistor is in cutoff region. Neglecting leakage current, all of the current are 0. IC is also 0. So because of that, VC will be equal to VCC. So that is the first equation, very important. VCE will be equal to VCC. So there is completely maximum voltage appearing across the output. Whereas in condition in saturation, when VB is equal to plus VBB, the base emitter junction is forward bias and there is enough base current to produce a maximum collector current. The transistor is saturated, and because of that, VCE is equal to 0. Okay, so that is the output in case of saturation region when the BJT is working in saturation. When BJT is used as an electronic switch, it is normally operated alternately in cutoff and saturation. Many digital circuits use the BJT as a switch. Okay, so let us see. That is a simple example what we explained now. So here we are making use of a BJT and we want to make a lamp glow. So here the external voltage source is given. Depending on that, so if we are giving a 0, means that is push button is open, then it is not glowing. But when you press it, or when we are giving the saturation mode, then it becomes glowing. So this is cutoff mode, not glowing. When it is saturation mode, it is glowing. Here the push button indicates how we are going to give the external voltage source. What happens when you give input external voltage source, and what happens when you release. Okay, so this is a simple example how making it a lamp glow. Okay, so let us see a simple application of a transistor as a switch. Okay, so here our purpose is to make a LED glow. Okay, so here it is also working as a switch, but how we are making it glow is by giving an input signal V in. We are going to give a square pulses. So square pulses is a periodic waveform of zeros and ones, and here we are taking a 50% duty cycle. 50% duty cycle means what? 50% if it is on state and 50% it will be off state. Okay, so that means T on and T off will be equal. Okay, so T on if it is 1 second, T off will also be 1 second. So 50% duty cycle. So that kind of square waveform we are giving it as an input. So what happens to this circuit when 0 pulse is applied? 0 pulse means what happens when input is given 0 means what happens? This comes in cutoff region. So because of that, will the LED glow? No. When we are giving 1, means it is high voltage. Okay, so because of that there is a voltage setup and there will be IB. Okay, so because of that the BJT will go to saturation region and the LED will glow. So the same concept how we have seen in case of lamp, here also it is using the same concept, consider a square wave input voltage with a period of 2 seconds is applied to the input as indicated, 1 second on and 1 second off. When the square wave is at 0 volts, the transistor is in cutoff, and since there is no collector current, the LED does not emit light. When the square wave goes to its high level, the transistor saturates. This followed by the LED, and the resulting collector current flow through the LED causes it to emit light. Thus LED is on for 1 second and off for 1 second. Okay, so understood the concept? So here this is how it works for an NPN transistor. When we are making when we are giving a 0, what happens? When we are giving 0, what happens? There is no current that is flowing because base current is 0, so there is no current. Because of that, output will be 0. But when we are giving input 1, what happens? The output starts glowing. Okay, so LED green light is visible. Now in case of PNP, it's the reverse. When you are giving 0, the output will glow. When you are giving 1, the output will be off. Okay, so this is how an LED is made to glow. Next, let us see the concept of feedback amplifier. Okay, so the application of BJT as an amplifier and switch is clear for you, right? Now let us see the importance of a feedback amplifier. The feedback amplifier can be defined as an amplifier which has feedback path from output to input. Okay, as the name indicates, feedback means what? There is a path from output to input. So what is feedback amplifier? It is such kind of amplifier which has a feedback path from output to input. So a feedback amplifier will consist of two parts. What are that? One is the amplifier part and one more is a feedback circuit. Okay, the feedback circuit usually consists of resistors. Okay, so different kinds of resistors will make it work as a feedback path. So here you can see a neat block diagram of a feedback amplifier. So we have the amplifier circuit, amplifier with gain A, and then we have a feedback circuit. Okay, feedback circuit with the feedback factor beta. Okay, so if you see here, source voltage is applied, right? Source voltage is applied, and here if you see out from the output, there is some part which is given back to this input, right? So output is taken and fed back to the input. Okay, that is why it is called a feedback amplifier. Okay, so the output which is arriving at this feedback circuit will be what? Will be here output. Let us take output voltage as VF. VF will be equal to, what is the input voltage here? So that the portion of output is taken, right? So that will be V0. And what is the factor, feedback factor, gain factor? That is beta. Beta times V0. So beta times V0 will be the output from this feedback circuit. Okay, so here the input voltage, source voltage is given, and considering its feedback, we are getting the input voltage. Okay, so now let us see the different types of feedback. Okay, so there are mainly two types of feedback, that is positive feedback as well as negative feedback. What is positive feedback means? If you are taking the output is given to the positive terminal of the amp, then it is a positive feedback. Here the output will be in phase with the input. In case of positive feedback, the output will be in phase. Okay, so whatever the feedback circuit, the output and the input and the feedback will be in phase. Whereas in case of negative feedback, since output is given to the negative terminal, input and feedback will be out of phase with each other. Okay, so in case of positive feedback, input and feedback will be in phase. In case of negative feedback, input and feedback will be out of phase. Okay, so from the figure, the gain of the amplifier is represented as A. The gain of the amplifier is the ratio of output voltage V0 to the input voltage Vi. Okay, the feedback network extracts a voltage Vf equal to beta times V0 from the output V0 of the amplifier. This voltage is added for the positive feedback and subtracted for negative feedback from the signal voltage Vs. Now we have to find what is the voltage. Okay, so if we are taking the positive feedback and negative feedback, we have to see what is the voltage we have taken. So if you are taking a positive feedback, then Vi will be nothing but will be equal to Vs is the input voltage, and if we are giving positive feedback means you are giving to the positive terminal, so it will get added up. Plus what is Vf? Vf is beta times V naught. Beta times V naught. Okay, this is for positive feedback. But in case of negative feedback, what happens? In case of negative feedback, Vi will be equal to, what is the source voltage? Vs. Okay, Vs minus beta times V naught minus Vf. Vf is nothing but beta times V naught. Hope this is clear. Okay, the same equation is written here. Now if it is a positive feedback, Vs, this voltage, the voltage is added for positive feedback and subtracted for negative feedback from the signal or source voltage. So Vi is equal to Vs plus Vf, that is Vs plus beta V naught. Vi is equal to Vs minus Vf, that is equal to Vs minus beta V naught. Okay, so we know the quantity beta is equal to Vf divided by V naught, that is called the feedback ratio or feedback fraction. Yes, so beta times V naught is equal to Vf, so beta is equal to Vf minus by V naught. Let us consider the case of a negative feedback. So output V naught must be equal to the input voltage Vs minus beta V naught multiplied by the gain of the amplifier. So Vs minus beta V naught into A is equal to V naught, or A into Vs minus A beta V naught is equal to V naught. A Vs is equal to V naught into 1 plus A beta. Right, so therefore we can write the ratio V naught by Vs is equal to A divided by 1 plus A beta. Okay, so this is about feedback amplifier. Okay, so if we take AF as the overall gain, then we can write as the gain with feedback as output voltage divided by input signal voltage. So the ratio of output voltage to the signal voltage Vs, that is the overall gain with the feedback. F is equal to output voltage divided by input signal voltage. So because of that, the gain of the feedback amplifier with negative feedback is written as AF is equal to A divided by 1 plus A beta. The gain of feedback amplifier with positive feedback is given by AF is equal to A divided by 1 minus A beta. So this is an important derivation for you to find the gain stability of negative feedback and what happens when you are giving the positive feedback. So derivation is important. So I hope that is clear for you how we have taken the derivation. Okay, so we know there are two types of feedback amplifiers, positive feedback amplifier and negative feedback amplifier. So because of that, using this equation we will get what is the ratio. So in case of negative feedback, it is A divided by 1 plus A beta, whereas in case of positive feedback, it is A divided by 1 minus A beta. Okay, so we'll continue the session in the next video.